Welcome to a Programming Languages virtual meetup pre-recording. My name is Connor Hoekstra, and in this video we're going to be covering the second half of chapter 3.5 of the structure and interpretation of computer programs. So in the last video we covered the first 2.5 subsections of the final section of chapter 3 entitled Streams. And in this video, we're going to be starting right where we left off in the middle of 3.5.3, exploiting the stream paradigm, and then we'll be covering the final 2 subsections rather briefly to finish this video off. So let's jump back into the middle of exploiting the stream paradigm. We ended at the following section, streams as signals. And the text says, we began our discussion of streams by describing them as computational analogs of the signals in signal processing systems. In fact, we can use streams to model signal processing systems in a very direct way, representing the value of a signal as successive time intervals as consecutive elements of a stream. And the book goes on to show a couple different examples, but we're going to jump straight into one of the exercises from this chapter subsection. And that is exercise 3.74, which reads, Alyssa P. Hacker is designing a system to process signals coming from physical sensors. One important feature she wishes to produce is a signal that describes the zero crossings of an input signal. That is, the resulting signal should be +1 whenever the input signal changes from a negative to a positive, -1 whenever the input signal changes from a positive to a negative, and 0 otherwise. Assume that the sign of a zero input is positive. For example, a typical input signal with its associated zero crossing signals would be, and if you look at the following stream, for the first little bit we have positive numbers, so we just get 0, 0, 0. Then when it goes from positive to a negative number, we get a -1, and then it's negative for a while, so we get zeros again, and then once it crosses back over from negative numbers to positive numbers, we get a 1. The exercise goes on to read, in Alyssa's system, the signal from the sensor is represented as a stream sense data, and the stream zero crossings is the corresponding stream of zero crossing. Alyssa first writes a procedure, sign change detector, that takes 2 values as arguments and compares the signs of the values to produce an appropriate 0, 1, or -1. She then constructs her zero crossing stream as follows, and we have the definition of zero crossings and make zero crossings. Alyssa's boss, Eva Lou Ader, walks by and suggests that the program is approximately equivalent to the following one, which uses the generalized version of stream map from exercise 3.50 using the following. So we're calling stream map to define zero crossings, passing it the sign change detector, sense data, and then a subsequent expression. And the exercise finishes by saying, complete the program by supplying the indicated expression. So really, if you sort of want to test this a little bit, you also need to implement the sign change detector procedure, which is the first thing we're going to do. And then we're going to test this out to make sure that our final zero crossings procedure is equivalent to what we had before with the zero crossings in terms of make zero crossings. So if we take a look at the answer that I have, you can see that I first tried to take the sense data that the exercise gives us to use this, but obviously this is going to be a list and not a stream, so we're not going to be able to use this due to the fact that I'm using the hash SICP language, which is very close to MIT scheme. If you are using Racket, however, they do have stream to list and list to stream, and scheme might have the same facilities, but if you're using the Racket/stream module, you can use this sense data and then just convert it to a stream using the stream or list to stream. However, I'm using hash SICP. In hindsight, I should have used Racket, but c'est la vie. So we just have a very simple stream that consists of 1 and -1, and we're going to initialize the last value to be -1. So basically we're going to expect to see a -1 to 1, which should give us 1, and then a 1 to -1, which will give us -1. So we have our sign change detector here, which is just going to take our current signal and then the previous one, and it's going to compare the two. So it basically reads, if we have 2 different cases in our first 2 clauses, we're going to return -1 and 1. So when the previous is greater than 0 and the current is less than 0, that means we've gone from a positive to a negative, so we return -1. And if it's the opposite of that, then we are going from a negative to a positive. We want to return 1. And if it's anything other than that, we want to return 0. And when we combine this with our make 0 crossings and we test the following, like we said, we start at -1, go to 1, which is the first value in our sense data that we have. We're going to get a +1, and then we go from 1 to -1, which is the second value in our sense data. We're going to get a -1. However, the question asks us basically to fill in the final expression of the definition of 0 crossings that uses a stream map, and we can set this up by basically using the same initial value, which is going to be -1, and then creating a const stream of -1 and the sense data. And once we've done this, we can test it out, and sure enough, we get the same answers. So pretty straightforward. All we have to do is basically come up with this expression to put into our stream map definition of 0 crossings, and then also define the sign change detector if you want to test it. Moving on to the next subsection, 3.5.4, streams and delayed evaluation. Once again, we're going to jump straight into an exercise to take a look at this subsection. So exercise 3.77 states the integral procedure used above was analog to the implicit definition of the infinite stream of integers in section 3.5.2. Alternatively, we can give a definition of integral that is more like integers starting from, also in section 3.5.2. So we have this definition of integral, which takes an integrand, an initial value, and dt, and then we have the following definition. The exercise goes on to read, when used in systems with loops, this procedure has the same problem as does our original version of integral. Modify the procedure so that it expects the integrand as a delayed argument and hence can be used in the solve procedure shown above. So this question is basically asking us to modify a procedure such that one of the parameters uses the delay keyword, similar to how the const stream procedure uses the delay keyword to delay the coulter of the pair such that we can define a stream. However, if we take a look at the code that the book presents us with that sort of leads up to this question, we have this integral with a delayed integrand. But when I tried to run this, it actually just said y is undefined, and there's a note in the book that says depending on the variant of scheme that you're using, you might need to tweak this code in order for it to run. So unfortunately, I wasn't able to get this code to run using the #sicp MIT scheme dialect that Dr. Rackett provides us with. But in order to solve this question, I was pretty confident that I wouldn't need to run this code, and I was able to spot check the solution that I came up with another one. So even though I wasn't able to run it, we can still answer this question. But a little bit irritating that the different variants of scheme sort of leads the code in the book to sometimes run and sometimes not run. But so this is the original code that the question gives us. We have our integral procedure, and we basically want to take the integrand parameter and set it up such that it is going to be only evaluated when we need it. So if we take a look at the solution, this is the modified code, so we can sort of see not much has changed. The only things that have changed are the following. We have a let expression that is evaluating the integrand once we get to this let expression, so we're then calling force. And up until then, we are sort of wrapping the stream coulter integrand in a delay. And like I said, I spot checked this with some code on a SICP solution site, and it was consistent with what I had. So pretty neat to see how we can use the force procedure and the delay keyword to set up some of our parameters to be only evaluated when we actually are using them, and not immediately as we would in sort of the applicative order model that we've been seeing up till now. And speaking of applicative order versus normal order, at this point in the book, the text reads, "The examples in this section illustrate how the explicit use of delay and force provides great programming flexibility, but the same example also shows how this can make our programs more complex. Our new integral procedure, for instance, gives us the power to model systems with loops, but we must now remember that integral should be called with a delayed integrand, and every procedure that uses integral must be aware of this. In effect, we have created two classes of procedures, ordinary procedures and procedures that take delayed arguments. In general, creating separate classes of procedures forces us to create separate classes of higher order procedures as well. And this brings us to an interesting and rather long footnote that talks about this in different programming languages. So the footnote reads, "This is a small reflection in Lisp of the difficulties that conventional strongly typed languages such as Pascal have in coping with higher order procedures. In such languages, the programmer must specify the data types of the arguments and the result of each procedure, number, logical value, sequence, and so on. Consequently, we could not express an abstraction such as map a given procedure proc over all the elements in a sequence by a single higher order procedure such as stream map. Rather, we would need a different mapping procedure for each different combination of argument and result data types that might be specified for a proc. Maintaining a practical notion of data type in the presence of higher order procedures raises many difficult issues. One way of dealing with this problem is illustrated by the language ML, which stands for meta language, whose polymorphic data types include templates for higher order transformations between data types. Moreover, data types for most procedures in ML are never explicitly declared by the programmer. Instead, ML includes a type inferencing mechanism that uses information in the environment to deduce the data types for newly defined procedures." So interesting to see how different languages like ML, Pascal, and Lisp sort of run into this problem and potentially solve it. And I'll definitely be looking more into ML, like I said, which stands for meta language, in the future, because ML went on to influence many, many languages, including Haskell, which is one of my favorite programming languages today. The text then goes on to read, "One way to avoid the need for two different classes of procedures is to make all procedures take delayed arguments. We could adopt the model of evaluation in which all arguments to procedures are automatically delayed and arguments are forced only when they are actually needed. For example, when they are required by a primitive operation. This would transform our language to use normal order evaluation, which we first described when we introduced the substitution model for evaluation in section 1.1.5. Converting to normal order evaluation provides a uniform and elegant way to simplify the use of delayed evaluation, and this would be a natural strategy to adopt if we were concerned only with stream processing. In section 4.2, which is coming up in just 2 chapter sections, after we have studied the evaluator, we will see how to transform our language in just this way. Unfortunately, including delays in procedure calls wreaks havoc with our ability to design programs that depend on the order of events, such as programs that use assignment, mutate data, or perform input or output. So look forward very shortly in a couple of videos. We will be covering, after we get into the meta-circular evaluator chapter, how to do this to our scheme dialect. And this takes us, last but not least, to the final subsection of chapter 3.5, modularity of functional programs and modularity of objects. So we jump once again straight into an exercise 3.81, and this states exercise 3.6 discussed generalizing the random number generator to allow one to reset the random number sequence so as to produce repeatable sequences of random numbers. Produce a stream formulation of this same generator that operates on an input stream of requests to generate a new random number or to reset the sequence to a specified value, and that produces the desired stream of random numbers. Don't use assignment in your solution. So I solved this in one of what could be many ways to solve this. So first I Googled for sort of a random sequence generator and found a Stack Overflow post that described a Knuth algorithm. And the Knuth algorithm that was provided by the Stack Overflow post, I believe, is a linear congruential generator, which is a simple algorithm to generate a pseudo-random list of numbers, and you just need to provide it A, C, and M with a seed. And this will give us the ability to sort of take any seed that the stream provides us with, and there has to be some requirements of like co-primeness between A, C, and M. But the details don't really matter. You can use any simple algorithm that generates a sort of random or pseudo-random list of numbers. And basically what's going to happen is our stream is either going to be the message, a new so like NEW for a new random number, or it's going to be a pair or a list of reset with a new seed. So it's not a really comprehensive algorithm, but it's going to check if it's a list. This is the case where we're getting a new seed, and we can get catter of our args to get that new seed, and then it's going to do the operation of dividing the seed by m. Otherwise, if we just get the new message, we're just going to perform the transformation to get the next number in our sequence in our LCG algorithm that was provided. And so once we have this, we define random stream to take an input stream of our messages and our new seeds for the reset message, and then we just stream map random over our input stream. And to test this, we can see we set up our sort of temporary stream. So this is just going to alternate between resetting our stream with the same seed that we had in our algorithm, but you can use any seed here and then getting a new number, and then defining R to be a random stream over this sort of back and forth of new and reset, new and reset. So what we expect is just to see the same two numbers over and over again. And sure enough, if we map stream ref over our random stream R, you see that we get the same two numbers here. So as the question asked, we have basically created a random stream with the ability to reset to the point that we started at any point in time, so that we get the same sequence of numbers after we've reset. The textbook then states, modeling with objects is powerful and intuitive largely because this matches the perception of interacting with a world of which we are a part of. However, as we've seen repeatedly throughout this chapter, these models raise thorny problems of constraining the order of events and of synchronizing multiple processes. The possibility of avoiding these problems has stimulated the development of functional programming languages, which do not include any provision for assignment or mutable data. In such a language, all procedures implement well-defined mathematical functions of their arguments whose behavior does not change. The functional approach is extremely attractive for dealing with concurrent systems. And this footnote we are going to read, and it comes from John Backus, which reads, John Backus, the inventor of Fortran, gave high visibility to functional programming when he was awarded the ACM Turing Award in 1978. His acceptance speech, Backus 1978, strongly advocated for the functional approach. A good overview of functional programming is given in Henderson 1980 and in Darlington et al. 1982. So note that this is, I guess, pretty recent because the book came out in 86, which is sort of referring to two resources that are only 6 and 4 years before, and this 1978 ACM Turing Award paper was only 8 years before the book was published. So they don't mention the paper by name, but it is quite a famous paper, and it's called Can Programming Be Liberated from the Von Neumann Style, a Functional Style, and its Algebra of Programs. I highly recommend reading it. It's a fantastic read, and interesting to see that sort of back in the 80s, they're talking about this sort of paradigm, functional programming, as becoming an alternative to the sort of structured or imperative programming that has been very popular since the 60s. And now that we are in 2020, which is 35 years later, functional programming is considered not one of the main paradigms, but definitely sort of the alternative to imperative programming at this point. And there are many functional programming languages that people, if they don't code in, at least they are quite aware of them. And the last thing that we're going to read is the final thing that this chapter 3.5 states, which is, we began this chapter with the goal of building computational models whose structure matches our perception of the real world we are trying to model. We can model the world as a collection of separate, time-bound, interacting objects with state, or we can model the world as a single timeless, stateless unity. Each view has powerful advantages, but neither view alone is completely satisfactory. A grand unification has yet to emerge. So that brings us to the end of Chapter 3. There are only a couple of things I want to highlight for Chapter 3.5, or the lectures that corresponded to Chapter 3.5. The first of which came from the MIT lectures. I believe it was 6B, and this was taught by Hal Abelson. He mentions Miranda as a language that a lot of research is happening in for the functional programming paradigm. And it's interesting that Miranda's mentioned because Miranda is a lot less well known compared to Haskell, which is now in 2020 considered to be the sort of research functional programming language. And I looked it up, and that's because the MIT lectures that were given by Hal Abelson and Gerald Sussman to Hewlett-Packard employees in 1986, at which point Haskell had not been invented yet. So Haskell first came onto the scene in 1990, and before then, Miranda was sort of the top language. And Miranda went on to highly influence Haskell, and if I recall correctly, the sort of early conversation around sort of centering on, getting different post-secondary institutions to choose sort of one language to do all their research in so that you didn't need to convert between different languages, was to sort of have like a Miranda 2.0. But then the creators of Miranda weren't a big fan of what was going on there, so they decided just to create a whole new language, but it was still heavily influenced by Miranda. So interesting to see Hal Abelson mentioning Miranda, that being due to the fact that Haskell hadn't been invented at this point in time. And there's a great bit from lecture 6B, I believe it was, where they talk about sort of the difference between normal order and applicative order, which is basically circling all the way back to chapter 1 when they first introduced these two topics. And then if we hop over to the Berkeley lectures, I think I mentioned this in the previous week's video about how it's a little bit difficult to visualize the implicit definitions of these streams. And it was fantastic to see that Brian Harvey from the Berkeley lectures explicitly pointed out this sort of, what I believe I referred to was this sort of triangular matrix approach to sort of visualizing some of these streams that are defined in terms of other streams. So he does it just in terms of two rows, but you can think of each of sort of the subsequent rows, you could just have each of the rows so you end up with like a triangular matrix of how you need to think of these things. So he did it once with ones and ints, and then another time sort of more generically with just constream and interleaving. But yeah, highly recommend checking out either of these two lectures, as it is a great supplementary resource. And with this, the last thing I want to say is that in the previous meetup for the first half of chapter 3.5, there was some awesome discussion, and there were a ton of links that ended up getting shared in the chat. And I figured I would put those links for those that are interested in the description of this video for anyone that wants to go check out any of these links that were sometimes just being posted because we were talking about tangents of the current topic of the chapter, and other times it was specifically relevant to something that was being covered in the chapter. And I should also mention that I believe in the previous video I was butchering the pronunciation of one of the greatest mathematicians in history. I was saying Euler, but that is the incorrect pronunciation. Someone pointed out that it is Euler, which I actually knew, but whenever I read it, I always think of Euler because of Ferris Bueller's Day Off. But it's not. It should be Ferris Boiler's Day Off, because Euler had such a profound impact on the mathematics that we know today. So remember, Euler is the way to pronounce this, and this lecture I went and watched right afterwards, after the meetup that we had on the Monday night, and it is a fantastic lecture and really impresses upon you how important and how large the impact that Euler had on mathematics. So definitely recommend checking out any of these links, especially the Euler history lecture. They'll be in the description in the links down below. And with that, thanks for tuning in. As always, I hope you enjoyed and I hope you learned something, and I hope to see you in the next video.